Welcome to Chapter 5, Lesson 4 in Stats. Conditional probability. So, conditional probability is the probability that one event happens given that another event has already happened first. So the probability of B happening given that A happens first is written as P of B given A, with that little vertical line in between B and A. The thing that you want to happen comes first, and the thing that comes first, the thing that has to happen before the thing you want, comes second. So the formula for that is the probability of B and A both happening divided by the probability of A happening. So again, that's either the probability of the intersection divided by the probability of the first event, or just the probability of both divided by the probability of the first one. So the next part is sometimes P of B given A and P of B given anything else happening first are the same. And that would mean that these are independent events. B and A are not actually related. So when the conditional probabilities don't change regardless of whether another event happens first, P given A happened first or P given A did not happen first, and both of them are just P given B, then A and B must be independent of each other. Give me 1 second to find my calculator. Okay, so students in a college statistics class want to find out how common it is for young adults to have their ears pierced. They recorded data on two variables, their age and whether or not they had pierced ears. We already looked at this example before, but now we're asking different questions. Suppose we choose a student from the class at random. If we know that the student has a piercing, what is the probability that they are also between the ages of 18 and 22? So we're looking for the probability that they are aged 18 to 22, given that we already know they have a piercing. So that's going to be the probability that they are 18 to 22 in general and have a piercing. Divided by just the probability that they have a piercing. Now, right now, we have whole numbers up here, so we're going to end up with fractions. So if they're 18 to 22 and have a piercing, that's 19 out of 178, and that's going to be divided by just all the people with a piercing, 103 out of 178. Now, one of the things that ends up happening here, because we're dividing by the same denominator in both cases, when we have 19 over 178 divided by 103 out of 178, that kind of ends up just being 19 out of 103, because 19 over 178 times 178 over 103 cancels your 178s. So there is a 19 out of 103 chance that, given that a person has a piercing, they might be 18 to 22. And 19 out of 103 is about a 0.184 chance, or an 18.447% chance. So if we know that the student is 23 or older, what's the probability that they have a piercing? So that one, we already know that they are 23 or older. So we want to see what the probability of having a piercing, given that they are 23 and older. So again, that's the probability of both a piercing and being 23 and up, divided by the probability of just being 23 and up. So again, probability that they are both, you have an 84 over 178 chance, and we need to divide that by, again, you could put this in the big fraction like that, or use it as fraction division horizontally. The probability that they are 23 or older is 88 out of 178. So we can turn this into 84 over 178 times 178 over 88. And then 84 over 88 will reduce. We can divide both of those by 4. So that's a 21 out of 22 chance, or a 0.955 chance, or a 94.455% chance. In 1912, the luxury liner the Titanic sunk on its first voyage across the Atlantic after striking an iceberg. Some passengers got off the ship in lifeboats, but many died. This two-way table gives information about the adult passengers who survived and who died by class of travel. Suppose we randomly select one of the adult passengers from the Titanic. F is first class, S is they survived, and T is third class. So find the probability that they are in third class and survived, given the probability that they survived. So the people who were in third class and survived were 151 out of 207. 1207. Out of total survivors, 442 out of 1207. Or again, we can kind of simplify that since we are going 151 over 1207 divided by 442 over 1207. This can become 151 over 1207 times 1207 out of 442. Again, the 1207s cancel, so we could have just said that this is 151 out of 442. I'm not sure if those will reduce, so let's check. Nope. So 151 divided by 442 is a 0.342 chance, or about a 34.163% chance. So given that the person is not a first-class passenger, what's the probability that they survived? So we are finding the probability that they survived given that they were not a first-class survivor. So again, that's just going to be the probability that they were surviving and not in first class divided by the probability that they were not in first class. So again, since we're all going to be dividing by fractions over 1207, we can kind of just find some totals here. So the people who survived and were not in first class were these 151 from third and these 94 from second. So 151 plus 94 out of the people who were not in first class. Well, altogether, again, there were 1,207 people, but 319 of them were in first class, so we will subtract them. And now let's simplify. 151 plus 94 and 1207 minus 319 becomes a 245 out of 888 chance, which does not reduce. So that comes out to be about a 0.276 chance, or a 27.590% chance that they survived. Example 3. A survey of all residents in a large apartment complex reveals that 68% of the residents use Facebook, 28% use Instagram, and 25% use both. Given that they use Facebook, what's the probability they also use Instagram? So the probability of using Instagram given that they use Facebook, is the probability that they use both Instagram and Facebook, divided by the probability that they just use Facebook, or that they use Facebook at all. Now this one, they already gave us the percentages, so we already know that 25% use both. And the probability of finding somebody who uses Facebook is 68%. So we can kind of cancel out our units of measurement there. 25 over 68 does not reduce. So that is about a 0.368 chance, or a 36.765% chance. And then finally, is there a relationship between someone's sex at birth and their dominant handedness? To find out, your textbook writers used the Census at High School's random data selector to choose a simple random sample of 100 Australian high school students who completed a survey. This two-ways table summarizes the data. So there we go. Are the events masculine and left-handed independent? So, explain your reasoning. If the probability of being left-handed, given that they were assigned male at birth, is the same as the probability that they were left-handed, given that they are not assigned male at birth, then the events are independent. We could also choose these the other way around, masculine given that they are left-handed. We can also check that. So the probability that they are left-handed given that they are masculine is the probability of both being masculine and left-handed, so that's 7 people total, divided by the probability that they are not masculine, that would be feminine, out of 54. So 7 out of 54. Oh, sorry, that was the complement. Sorry. If they are left-handed and not masculine, that would actually be the 3 out of 54, as opposed to the probability that they are left-handed and actually are masculine, or were assigned so at birth, would be the 7 out of 46. Since the probability of being left-handed given that they are not masculine is not the same as the probability that they are left-handed given that they are masculine, these events are not independent. Again, we can also check the other way around, the probability that they are masculine given that they are not left-handed, or that they are left-handed. Let's do are left-handed first. So that they are both masculine and left-handed would be those 7 out of just the people who are left-handed would be 7 out of 10. And the probability that they are masculine given that they are not left-handed would be this 39 out of the people who are not left-handed, or 90. And those are also not the same. So again, these events are not independent of each other. And that was our lesson for today.